So before I get started, I'd like to say thank you to Signify and Ryan for reaching out to invite me to give this talk and speak amongst such a stellar cast, what we've seen today and what's to come for the rest of the evening. So thank you. A little bit about myself. So I'm an engineering manager. I work at CS Services. I've been on and off in a contracting role since 2018 and joined full-time earlier this year. So what I'll be covering in this talk is a little bit about us, what the company does, our products, to kind of set the scene for some of the things that we'll be touching on later on in the talk. I'll be presenting the Chatroulette protocol, or a simplified version of it. And I'll be talking streams and how, our architecture, both on the front end, on the back end, is based around streams and finite state machines. And we'll also be touching on scaling an architecture like this, specifically scaling WebSockets, and I'll be making a case for Apache Pulsar for that particular use case. So about us, Chatroulette was kind of invented by one person back in 2010, Andreas Koestler. We currently have about 4 million users, about 1,000 users online at any one time. Chatroulette is a social media platform that enables people to communicate via a peer-to-peer video connection, for those of you who don't know it. If you don't know it, I encourage you to Google South Park and Chatroulette, and you'll get a bit of an idea of what it is. Now, in all seriousness, there's enough information out there to get you going. Apart from the main product, we develop a bunch of adjunct capabilities in-house around augmented machine learning and adult content detection, and how these kind of models, machine learning models, feed into our moderation pipeline. But this talk's not concerned about this. So the Chatroulette protocol. So this is Chatroulette, the unicorn factory. We don't produce unicorns, but we produce encounters between people, valuable encounters and fun encounters. So let's imagine a punter comes to the site. Let's call him Tony. And he wants to be matched with another punter that comes to the site. So he expresses his interest in being matched with someone. Packets, like, put some information about his client, about himself, and forwards that to Chatroulette. Then at the same time, or the later time, another punter comes along. Let's call her Lisa. And she wants to do the same. So on her end, she again does the same. She provides some information about herself and forwards that on to Chatroulette, which has a matching pool, but I think in this talk I'd call it magic pool, that will connect these two people and forward the respective information to the other peer. And then basically magic happens. So that will then enable people to communicate via a peer-to-peer video connection. And in theory, Chatroulette's role is kind of done at this stage, but it's not true. So this talk will mostly focus around this handshake we just saw, and how this is implemented in a scalable way for Chatroulette. So a little bit of theory. Our client and server, or user and application, are basically modeled by a set of interacting state machines. There's two here, but in reality, the system consists of a few more, but for the purpose of this talk, that's fine. And there's some kind of faulty and dumbed down versions of a user and a application state machine to the left and to the right. What's important there is you see a bunch of messages or actions that are prefixed by either a plus or a minus. The ones prefixed by a plus means we're receiving this kind of message. The ones prefixed by a stop means we're sending this kind of message. And now if you look, for instance, into the waiting state on the left-hand side and the matching state on the right-hand side, and the stop state, the transition to the matching state on the right-hand side, you see, the left-hand side emits a waiting for partner, the right-hand side receives a waiting for partner. So this basically means the two, the state machines are communicating with each other. They can't be looked at in isolation. To formalize this a little bit, for a number of processes N, we have S being the sets of states for each process. We have the O's being the initial element or the initial state for each process. And we have the M, I, and Y, which means the message is sent from process I to process Y, and the inverse for Y and I. And we have the step function to advance the state machine. This for tuple is called a protocol. We're currently investing some time in leveraging a formalism like this to kind of formally, I'm not to say prove the correctness of our protocol, but gain confidence about the correctness of our protocol. A bunch of people are investing time into this at the moment, but this is something for another talk. What I want to focus at is, how this how these state machines communicate with each other. So the short answer is it streams all the way down. On the client side, we use RxJS, which has a model of stream. On the server side, we use FS2. On the client, there's a bunch of streams, but most important one would be, for instance, stream of user actions and the stream of server actions that come via WebSocket. And conversely, on the server, we have a stream of client actions coming through a WebSocket and a stream of events, which might come from downstream systems that interact with our WebSocket server. So how does this look like on the client? So, we have Lisa here interacting with the site. So there's a stream that we can subscribe to user inputs. Like I said, the server input through a WebSocket. Then we have the client state machine running over this input and, pushing events to the user output, which, might apply changes to the DOM, or the server output, which goes back to the server, the WebSocket server. Now let's look at what this looks like on the server, and you'll immediately see the symmetry here. We have basically the same thing. Through the WebSocket input, we get the output of, or one of the outputs of the client-side state machine. The rest of the system can interact with the WebSocket or the server state machine through its input stream, and the output can be pushed to either both or neither. So how should I say? So there can be any number of events to any of the streams. So really, this shouldn't be called finite state machine, but finite state transducer. But I think for the purpose of this talk, it's fine. So what I mean is this might not produce any events, and it might produce one or more on each of the streams. Let's look at some code. So this is basically what our server-side state machine looks like. If you look at the transition function, it's just, you know, state input, state output, and then run is where it transforms a stream of inputs into a stream of outputs, given an initial state. So, you know, this is literally taken from production. There's a bunch of other operators that deal with you know, transforming state machines, but this is kind of the essence. And then some pseudocode as to how you put this all together. You know, the important bits are the types defined at the top. So we have state, we have client to server, which is exactly, you know, the messages from client to the server, responses from server to the client, and then event messages, you know, exchanged by the backend and the downstream systems. And so then we can define our input to the server state machine, which is either, you know, coming from the client, so it is a of type client to server, or it comes from the backend, so it's a type of event. Output is server to client. In this case, we're not dealing with events, just for this example. And this here, the logic, this would basically be the application logic, and it is just that. So it's a pure function from state and input to state and output, and most of our services are defined this way. And events are, you know, a stream of input events wherever they may come from. I'll be talking about where they may come from in subsequent slides. And then you're basically just creating the WebSocket builder, the WebSocket from the sending and the receiving queues and pipes. There's no magic there. The interesting bit is that either here, so you know, the events that come in from the WebSocket, either the events coming from the server, and you know, that corresponds to that either type up here, and we just run the logic. That's it. There's not much more. I mean, it's packaged up a bit differently, but there's not much more to it than what's shown here. So, scaling WebSockets. Remember Tony. So how does Tony's offer get to Lisa? As long as both Tony and Lisa have a WebSocket connection, so there's a typo there, open, we just pass it through, right? That's easy. The problem though is that this won't scale because the server only knows about clients connected to its own instance. So once we have more than one instance, this will obviously break down. So there are solutions to this. I mean, one could be some sort of router that knows about the WebSocket server instances being open. Another common one would be to introduce a comms channel between the instances, and for that, any PubSub technology will do. But as I'm hoping to show in this call, in this talk, is that some PubSub systems are better than others. So enter Apache Pulsar. So there's a bit of marketing talk. By the way, I don't have an affiliation with Pulsar, so I can pull off the marketing talk, but you know, it offers basically a queuing and the streaming model with you know, low message latency. I think the numbers there are that the latency is up to 2.5 times lower than Kafka for a similarly configured cluster. High throughput, I think the figure there is 40% higher throughput than a similarly configured Kafka cluster. Zero downtime upgrades, now that's where it starts becoming a bit more interesting. So you can add and remove bookies, you know, or add bookies with zero downtime. There's no rebalancing happening. New bookies just start picking up new work. And yeah, like I said, a unified queuing and streaming model, which is interesting if you also think about, you know, analytics pipelines and things like that. So it's kind of a one-stop shop in that sense. And now the reality, and you know, Pulsar has some killer features that make it very very useful for the use case we have in mind here. One is it supports fast topic creation on pub/sub, meaning, you know, there's no requirement to create a topic before a subscriber can subscribe or a publisher can publish to it. So they get created on the fly. I know there's some configuration options in Kafka that allow you to do the same thing, but kind of paired with the next point here, the garbage collection of unused topics, which, as far as I know, Kafka can't do. There's an open ticket requesting that kind of feature, but it's not implemented yet. So combined with the garbage collection on topics that don't have any active subscribers anymore, this is actually really cool feature. So it allows you to basically create a Pulsar topic per WebSocket connection once the client goes offline, unsubscribes from that topic, and the topic gets garbage collected. And another cool thing about Pulsar is it's been designed to support many topics. So there's talk of millions of topics per cluster, which is a slightly different model to what Kafka offers, where, you know, you usually have less topics that are partitioned, and you get, you know, you parallelize through that. So if we were to think, you know, doing the same thing, scaling WebSockets with Kafka, which is entirely doable, you'd be thinking of something like having one consumer group per WebSocket server, and then you just receive all the messages on all the WebSocket servers and filter by the ones that are relevant to your instance, and then, you know, route to the peers. So, you know, there's some extra work required doing the filtering. So ultimately, it will hamper horizontal scalability. Whether, you know, it will become a serious issue soon, it's a different story. But, you know, with Pulsar, you just don't have these problems. So how we do this is, you know, pair WebSocket connection. Like I said, we subscribe to a unique topic, which the topic name is derived from the WebSocket ID, which is, you know, just a UID. On WebSocket closure, we unsubscribe from that topic. The topic will garbage collected. That's it. So that's simple. Zero admin involvement, nothing. So also, you know, no routing, no filtering of messages. Like I said, they all find the right destination by virtue of being on the right topic. Also, there's shared state. Everything we need to know to write those messages, route those messages, is contained in the actual topic name. So this will get us towards the end of that talk. I left a little bit of time for questions in the end. If you want to learn more about communicating finite state machines or interacting finite state machines, how they're called sometimes, this article is a good primer. Neutron is available on GitHub. It's our FS2 Pulsar bridge to integrate, you know, FS2 with Pulsar, basically. And if you want to reach out, we have a couple of channels that you can do so. You know, we regularly blog on our engineering blog. There's Twitter, obviously, and there's LinkedIn. So this is basically it. If you have any questions, please shoot. I'm going to be available for a few more minutes, and then moving on to the